Have you ever wondered how cocoa is transformed into chocolate? Today, we will explain how the chocolate products that everyone knows and loves gains their appearance, taste, texture, flavor, and aroma. Humans generally evaluate these characteristics through participation in a sensory panel. Typical judgments are on appearance, taste, mouthfeel, flavor, and aftertaste. Multiple samples are generally compared as it is considered to be the most accurate method of judging quality. Laboratory experiments can also be conducted to judge textural and rheological parameters. The desired appearance of chocolate is consistent brown glossy color. The preferred taste is sugar, small amounts of salt, and minimal bitterness. Texture is the most complex of the quality parameters. The main focus of this particular aspect of chocolate is on smoothness, meltiness, and hardness. Smoothness depends on the particle size of the chocolate. Meltiness and hardness depend on the crystal structure and fat content. Finally, in terms of flavor and aroma, several different traits are desirable, such as acidity, bitterness, and to some extent burnt, caramel, and honey flavors and aromas. The first step in the chocolate production process is to select the genotype of the cocoa plant that is to be grown. There are three main varieties: Forastero, Criollo, and Trinitario. These varieties are labeled as bulk and fine grades, respectively. The genotype of the plants and the condition under which they were planted, such as soil conditions and climate, will influence the flavor of the final product. The next step in the process is fermentation. This process is generally carried out near the cultivation site and makes use of indigenous microorganisms. It is responsible for initiating the development of flavor precursors, and without it, the cocoa will never develop a chocolatey taste. To begin the process, the cocoa pods are split open, exposing the pulp and cotyledon, or nibs, to the bacteria present in the environment. There are two stages in fermentation, an anaerobic phase and an aerobic phase. The anaerobic phase is dominated by yeast for the first 24 to 36 hours. They break down sugars, such as glucose and fructose, into alcohols, such as ethanol and other derivatives, such as acetic acid and carbon dioxide. They also generate volatile compounds that influence the flavor and aromatic properties of chocolate. Research has shown that this is the most important step in the process. As the pulp ferments, it creates voids which allow air to enter the mass. This aeration, in combination with the fermentation products generated, inhibits yeast activity and allows the aerobic phase to begin. In the aerobic phase, lactic acid bacteria and acetic acid bacteria are involved. First, the lactic acid bacteria cause a temperature increase to 45 degrees Celsius by the third day of fermentation. However, one study that was conducted calls into question the importance of lactic acid bacteria, as when its activity was inhibited, it had no significant impact on the quality of fermentation or the quality of the chocolate produced from that fermentation. After the lactic acid bacteria decline, acetic acid bacteria take over and oxidize the ethanol into acetic acid and then to water. All these steps cause key components for flavor development to diffuse from the pulp into the nibs or cause undesirable astringent and bitter compounds to diffuse out of the nibs. A successful fermentation is denoted by nibs that are brown in color by the end of the process. The quality of fermentation is affected by pH, duration, and the mode of fermentation. The optimal pH range for cocoa beans is between 5.2 to 5.49. The optimal duration is 6 days for the majority of beans. With respect to mode, fermentation is most successful when performed in heaps covered by banana leaves and least successful in plastic boxes. Wooden boxes perform somewhere in the middle, but closer to the performance yielded in heaps. The second step in the process is drying. The most important thing is to avoid drying the beans too quickly, as this will cause excessively acidic and bitter nibs. After fermentation, beans contain approximately 60% moisture, and this must be reduced to 7 to 7.5% in order to inhibit mold growth and to preserve the quality of the beans during transportation. There are two main ways to dry cocoa beans: in the sun or artificially. Of the two, sun drying has been found to be the best drying method. However, artificial methods must be used in countries where there is a lack of dry conditions during the cultivation and fermentation season. Artificial drying can be conducted in a shed with air circulation or using fire. Fire is the most undesirable way to dry beans as it gives them a smoky taste. Drying also causes the beans to further develop a brown color. The third step in the process is roasting. This is a key step where the flavor and aroma precursors generated by fermentation are transformed at high temperatures through Maillard reactions to actual flavors. It also causes further loss of volatile substances that contribute to acidity and bitterness. The fourth step, which is optional and can occur in tandem with roasting, is alkalization, also commonly referred to as Dutching. Its purposes are threefold: to obtain further brown coloration, to further reduce bitterness and astringency, and to prevent cocoa powder from sinking in cocoa-based drinks. Different alkalizing agents that have been used are ammonium, potassium, calcium, magnesium, sodium hydroxide, magnesium oxide, and sodium bicarbonate. This process can be carried out on nibs or cocoa powder, which is heated along with the alkalizing agent with air if reddish cocoas are desired, or without air if darker cocoas are desired. The fifth step in the process is nib grinding and liquor treatment. At this step, the nibs are ground into cocoa liquor. The purpose of this step is to lower the viscosity of the mixture to form smooth cocoa powder. This will help develop the chocolate taste in the final product. Common machines used for this step are stone mills, disc mills, and pin mills. Stone mills are the most common as their slow turning ensures gentle handling of the cocoa. The sixth step in the process is mixing. At this stage, additives such as sugar, milk, cocoa butter, lecithin, and vanilla are added to cocoa powder and or liquor. This mixing can be carried out in batch or continuous mixers. In batch mixers, the ingredients are generally mixed for 12 to 15 minutes at 40 degrees to 50 degrees Celsius. These additives and the quantities in which they are added depend on whether milk, white, or dark chocolate is being produced. The seventh step in chocolate manufacturing is refining. At this stage, the particle size of the chocolate is reduced. A good chocolate product has particle size between 15 and 50 micrometers. Below this range, the human tongue cannot distinguish a difference in texture, and above this range, chocolate takes on a gritty feel. The ideal particle size is between 15 to 30 micrometers. For example, traditional European chocolates are in the range of 15 to 22 micrometers, which results in a creamier taste and better textured product. Refining equipment consists of 2 to 5 rollers, which the chocolate mixture is passed through at a specific temperature. This temperature is maintained with water coils in the rollers. The chocolate is attracted to the rollers by lipid and fat particles that remain on their surface, causing the chocolate to form a thin film. The lipids also absorb undesirable volatile compounds in the chocolate. The particle size distribution can be measured by laser diffraction. The distribution in the chocolate also has an important impact on the viscosity of the product. Studies have shown that a 60 to 40 ratio of coarse to fine particles generates the lowest viscosity. Conching is the eighth and second last step in chocolate production. At this stage, chocolate is agitated at a moderate temperature of 50 degrees Celsius or greater for several hours. This reduces the moisture content of the chocolate and further removes volatiles generated during the manufacturing process. Conching also helps develop a caramelized flavor in the chocolate, as sugars are exposed to elevated temperatures for long times. This step helps to refine the particle size, further reduce the viscosity of the mixture, and remove edges from the particles. Tempering is the final step in the process and is often viewed as the most critical. This stage consists of sharing the chocolate at controlled temperatures in order to promote crystallization within the chocolate. The substance that crystallizes is cocoa butter, which has multiple forms, some more stable than others. The most desirable form is form 5, which gives a glossy appearance and generates a snap in the final product. This process has 5 main stages which will differ operationally in terms of temperature and duration depending on the type and contents of the chocolate. First, a pre-crystallization step occurs to form seed crystals to promote better crystallization. Second, the mixture is fully melted. Third, controlled cooling occurs until the crystallization point where the temperature is held constant. Fourth, crystallization occurs. Finally, the last stage converts unstable crystalline forms to the most stable form. Over-tempering causes product hardness and stickiness, reduces surface gloss, and causes chocolate to darken. It also causes the melting point to shift to higher temperatures. Under-tempering is considered to be more severe, as it has greater impacts on texture, color, and surface gloss. It also causes flat bloom, which is denoted by surface whitening and changes in melting temperature. To summarize, all of the steps presented above play a key role in the quality parameters of the final chocolate product. The cocoa bean genotype plays an important role in establishing initial flavor. Fermentation develops key flavor precursors and removes some of the astringency and bitterness from the cocoa and begins developing the brown color of the beans. Drying significantly reduces the moisture content of the beans to preserve quality and further develops the brown color. After drying, roasting is undertaken, which further develops the flavor precursors formed in previous steps. Alkalization occurs along with or after roasting and aids in providing a brown color to the cocoa and further reduces astringency and bitterness. Nib grinding and liquor treatment transform the nibs into liquid form and helps develop chocolate flavor. Mixing occurs once the beans are transformed into liquor. Different additives that have an impact on flavor and rheology of the mixture are added at this step. After mixing, refining occurs. This step reduces particle size of the chocolate, which plays an important role in its texture and also aids somewhat in developing flavor. After refining, conching removes undesirable flavor compounds from the mixture and develops caramelized flavor in the chocolate. It also helps to further develop the texture. Tempering is the final step in the process. At this stage, a crystal structure is developed, which has an important impact on the hardness, meltiness, smoothness, and appearance of chocolate. Potential areas for further research on this topic include examining the role of acetic acid bacteria and other microorganisms in fermentation, performing studies on the industrialization of fermentation and drying, studying the effects of sun lamps on drying, performing optimization studies on the roasting process, performing studies to determine the most effective alkalization agent, and further studies looking into the mechanisms by which conching affects chocolate properties, as this is not well understood. We hope that this presentation gave you a better insight into how chocolates are made and to develop a better appreciation for this seemingly simple product.